I am very glad to introduce our next speaker. It is Professor Volin from University of Uppsala. Will speak about analytic beta ansatz.
Thank you for coming. I hope you enjoyed your dinner yesterday. So my talk actually called analytic beta ansatz plus. Because the word analytic beta ansatz was coined by Nikolai Reshetikhin at the time. Now all Soviet integrability school was not so old, and it actually was in Soviet Union, and I probably was not yet born. So this was about how to solve either beta or Coxeter equation by looking at some analytic properties. Well, we will do modern update about this. We will also solve the same equations by looking at some type of analytic properties. And if you not survive until the end of the talk, let me tell you one message now. So nested beta equations is a famous one, and for arbitrary rank, the algebra was proposed by Reshetikhin. Well, they are very great equations with a lot of insights and potential. But what we learned, they're actually not the most rigorous and not the best for efficiency equations to solve. So there is something which we can do actually better, and these are different equations. They describe the same system, but, well, they have some benefits, and we will speak about them. I can introduce the topic in many different ways. Every time I give talk, I do it in different way, and today I'm kind of, for myself, accomplishing some cycle. I'm going back to when I was like about 10 or 15 years ago in reality. And one way to do this is to consider what is called Hirota equation. So let us introduce notations. So in almost everything I'm going to speak today, functions will be functions of spectral parameter. So every time I will write some function, accept with some label or number, it will be a function of spectral parameter, which I will call u. And a model example to which you have to think about is just complex plane where u lives, and you restrict your attention to some strip. So you consider u inside, where your function is like holomorphic, there is no problems at all. And moreover, I know somehow that whatever I'm going to solve will be also having this property. So it's a very nice strip. And in this strip, we can, without problems, without any reservations, make analytic continuation by I. And when I write plus or minus, it means that u was shifted by this I over 2 or minus I over 2. So the difference is exactly one quantum of shift. And universal notation is that f with brackets n is f evaluated at u is f of u plus in over 2. So y over 2, because everything will be like bipartite. There will be even guys who has to be shifted by integer amount, and odd guys who will be shifted by integer plus 1/2 amount. So this is universal notation, and this plus and minus, well, is this example of this notation. And now we have index labels A and S. Well, these are discrete labels. What they are doing? So index A labels nodes of Dynkin diagram. So today we will do ADE. The status is following. A is old story, D we proved, and T, well, you can guess it's conjecture, and also you can get techniques behind, like A is determinants, D is functions, and E it's roots axiomatics and so on. And techniques every time is actually quite different. So this will be 3 series. This extends beyond ADE, but it will not survive till the end of this talk. Time will end up before I will be able to say anything about a non-simple list. So A just labels node on the Dynkin diagram. Well, this is D series Dynkin diagram, and S is going to label other direction. So you take your Dynkin diagram and you populate and you translate, like copy translate it infinitely many times in both directions. And so this is the direction of S. Let's say this is 0, this is 1, this is 2, and so on. And model problem when S is infinite in both directions. But then after you solve this model problem, you can start putting boundary condition. There's option to make boundary on one side. There's option to make boundary on both sides, some periodicity. It comes later. So model problem when S goes to infinity in both directions. So this is Hirota equation. It's defined. T is just called T function. No need to think about physical interpretation. But there are, of course, many physical interpretations. Like example is when there is eigenvalues of transfer matrices, or even just transfer matrices themselves for some spin chains. It can be T functions coming from Y system of thermodynamic Bethe for sigma models. So this can be some spectral determinant interpretation and many other interpretations. In reality, well, one rather famous, well, let's say just famous scientist, which I made a quote about 15 years ago. Well, in Russia, when you try to do any political regime, you end up with communistic party. And in integrability, whatever you try to do, end up with Hirota. And so our goal is to solve this problem. Today we're going to solve Hirota equation in terms of certain amount of, well, few functions. And think about this as a main combinatorial goal today. Analytic goal today is to solve Bethe equations, but combinatorial goal is to solve this Hirota equation. Tilde. Right. B means nodes adjacent to node A on Dynkin diagram. Yes, product of such nodes. So it's either 2 or 3 terms in this product. Yeah, thank you for the, I forgot to say thank you. Okay, so let us start. First half of my talk, I'm going to introducing standard theoretical background. It's just textbook, but those who do not know about flags in detail will appreciate that I do this. And those who know about flags in detail, I ask you still to listen. So there is a reason, because while I'm explaining basic things, I also introduce notations that I need. And I'm not sure you know notations that I'm going to use, because it's, well, like local community notations. And also some ideas which may be shown in new light. Right, so what we will have Lie algebra of ADE type. It will have rank R. And, we will need the minimum thing we need to introduce. We have Chevalier generators of Lie algebra. So we have raising operator, lowering operators, and contents of algebra. And as well, we will need fundamental weights. So what are fundamental weights? Well, Cartan generators form basis in Cartan algebra, and fundamental weights is a dual basis in the dual space of roots. And what is the standard knowledge? That arbitrary weight is a linear combination of over the basis. Coefficients are called Dynkin labels. And in all finite dimensional representation of highest weight type, and for being highest weight, for being irreducible finite dimensional, this Dynkin labels of highest weight should be non-integer positive. So dominant integral weight. Right. And what we else need? We introduce L of omega. So this is vector space of irreducible representation with highest weight omega. And notation, and we explicitly introduce a basis in the space. We introduce weight basis, the one which generalizes Cartan generators. And this basis is going to be labeled in quantum mechanical way, 1, 2, 3, and so on, up to dimension, up to D, where D is the dimension of your representation. So how to exactly introduce this basis? This will be completely omitted. The only thing you need to know that it is weight basis, and that there is a convention that 1 is correspond to the highest weight. So this means the following, that E acting on 1 kill it, and HA acting on 1 produce you back these Dmytro labels. So this information actually defines for your representation. And after introduce this basis, let us consider vectors in the space. So vector can be expanded in a basis. And we will think about x1, x2, and so on as homogeneous coordinates inside projectivization of our vector space. So we introduce a projective plane here, and coordinates of our vector will be thought as coordinates on the space. There is one special point on the space, let's call it O small, which is 1, 0, 0, and so on. So this is a point corresponding to highest weight. And of course, G, all right, so G is this exponentiation of our Lie algebra. And G acts on the space. And now you probably may start feeling happy because you have projection space, action of group, is in a homogeneous space, and so on. No, so this action is not it's not a homogeneous space with respect to this action of G. It's homogeneous space when we speak about SLD action. G is a very different group, and representation is some representation of it. And so there are two important messages. Message number one, the action is not transitive. We do not go from any point to any point, and it is non-free either. So let us do two examples to explain what the action is non-transitive. These examples will stay with us to the end of the talk, because on them I will introduce later all structures for examples of analytic bit ansatz. So example number one is just a series. So we denote it as Ln. And well, how we denote the Dmytro diagram? Well, you can guess how. Just labeling of nodes is from left to right. And so what is our representation? Well, vector space V will be identified with first fundamental, and it's just the one, the standard one, the most known one. And for this case, it's this nice homogeneous space when G acts transitively and so on. But then we have, for instance, lambda 2 of V. This is L of omega 2, and so on. All high fundamental representations will be just exterior parallels of V. Okay, so what is the highest weight for each representation? For the first fundamental representation, highest weight is denoted as E1, and E1 is a standard basis vector in Cn. Right? The one who has 1 in the first position and 0 everywhere else. So standard highest weight vector here is E1 wedge EV2. Where E2 is the second basis, standard basis vector. Highest vector here is E1, which E2, which is 3. Well, and I hope you got the drill from now on what happens till the end of the picture. Right. And the point that if you take G and acts on E1 understood as vector defining point in the projective space, well, this action is transitive. This is fine. This is exactly normal quantum mechanics. This is no fun. Now, starting from here, it is no longer transitive. So, with a very simple reason. So, coordinates on exterior of a square, what is this? It's two forms. So, not every two form represents for you a two-dimensional plane, right? But G orbit of highest weight is clearly wedge of two vectors representing hence two plane. So these are only these two forms which are happening to be on the G orbit, and this is a good example of being non-transitive. Right? So this is our first example. And example number 2 is this series. For the D series, diagram is like this. The enumeration from the left, then to the right, r minus 2, r minus 1, r. So the first fundamental is still a vector space. Now it will be of dimension 2r, so quite bigger, quite larger than the rank of the algebra. Then you go down and you will have up to r minus 2 just exterior power of v. So this is like in GLN, details is in SLN, details slightly different. But then we also have two fermionic representation. Let us call it W, which is L of omega r minus 1, and WC. So these are two Weyl spinors representations. We'll speak about them later. Let us just focus on vector representations, tensor representations so far. So here again, E1 is a basis vector. E1 is a basis vector. It's the same story. But now we have extra data. Well, you know, in orthogonal groups, we have bilinear symmetric form. It's defined through it. And so basis vectors in our space should be labeled EA, E plus minus A. A goes from 1 to R. And the condition that EA with E minus B, this bilinear form of this combination is Kronecker delta. And EA, when we speak about the same sign of A and B, then it is 0. So this means that this vector is null, right? It's not arbitrary vector, it's null. And well, physics corresponds to like complex version of light cone basis in our Minkowski space. Okay. So the point that G orbit of null vector will be always null vector. So here now, even in for fundamental representation, we do not have transitive function. Okay, so we concluded that G is non-transitive. For us, it's not a big deal because actually only thing we want G orbit of our origin. This is the only thing we care about. So in this sense, it's transitive. It's transitive on the orbit of the origin. But then the G is also an action of G is actually also not free. G action is not free. And because I mean, our origin has a stabilizer. So let us just describe the stabilizer. Well, on the level of Lie algebra, what we have? Lie algebra, which stabilizes our highest weight, well, it's generated by all raising operators because they kill highest weight. It's preserved by Cartan because we are projective. But then we also have to add lowering operators. Which ones? Those for which corresponding Dynkin label is 0. So why so? Because when Dynkin label is 0, this is a C2 subalgebra. Well, you get trivial representation, so they will have to act trivially. And so this is our stabilizer. And so let us introduce more accurate notation, because we're going to need this. Let us introduce A, which is multi-index. Well, let us introduce PA. So A here is a multi-index from labels on Dynkin diagram. And we defined PA as all EAs generated by all HAs, but also all FB such that B is not in A. Yeah, so this counterintuitive notation. If index A is here, FA will be not there. Right? And then, of course, we want to introduce a corresponding group, PA, so exponent of the algebra. And this is called parabolic subgroup. And g-orbit of origin is what it is. It is a G quotient by stabilizer. And this is called parabolic flag manifold. Yeah. So this is where we have get two flags. Okay. So now we have to think about these coordinates as generalized Plücker coordinates. And you have to understand this as extensive coordinates. There's much more coordinates than the dimension of the space, but then they satisfy relation. It's called Plücker relation. So on the first example that we had, like if you have two forms, it's a Plücker, like original Plücker relation, two form is 0. It's a Plücker quadrix. On the second example, the fact the vector is null means that V scalar product with itself is 0. It's another bilinear relation. So we have many coordinates satisfying some relation. So, well, two form is Plücker is okay, but vector V being null understood as Plücker relation, well, it depends on your background. Now, this is true for, we'll have Plücker relations for any nodes. And for example, number 2, let me now introduce also what happens with spinors. So to introduce what happens with spinors, let's keep going with our picture. So we end up to E1 wedge E R minus 2. Actually, for this case, let us do it shorter. Let us just do this one. So a SO8 example will be enough to understand what is going on. So we have E1 wedge E2. So what is E1? It's a space of null vectors. E1 wedge E2 is called isotropic subspace. It's a space in which any direction is null. I mean, g-orbit of it, I mean. And then we actually have to add two more nodes. Let's put it in blue. So this is a node of the Dynkin diagram, but this corresponds to representation whose highest weight vectors is E1, E2, E3. And we have two extra nodes. Here we have E1 wedge E3 wedge E4, and here I have E1 E3 E minus 4. Okay, so this is just again isotropic plane of dimension 3, g-orbit of it. And now we have two different gadgets. Who are they? Well, these guys are all maximal isotropic plane corresponding to self-dual representation, and this is anti-self-dual representation. There are we split into two classes. And so the point that this is actually a representation correspond to L of 2 omega r minus 1. And here we have, of course, L of omega r minus 1. So g-orbit of this g-orbit of highest weight here is the same as g-orbit of highest weight there, like they coincide. And so actually, what are spinors doing for us? They describe for us maximal isotropic spaces. Self-dual and tensor self-dual. That's what spinors are doing. And so this is a space of dimension r. Well, let's do it 4 in 8-dimensional space. So 4 in 8-dimensional space is half the way through. This is another 4 in 8-dimensional space. Now, what happens when two hyperplanes of dimension 4 and 4 intersect? Well, usually intersect by a point. But if you consider tensor product of this representation in G-orbit, it means that corresponding hyperplane intersects by a plane of dimension 3, r minus 1, and this will be this plane. So conditions, they both belong to the same G-orbit of highest weight simultaneously. Is conditions, they intersect on quite a big subspace, and this corresponds to G-orbit of this point. And how this looks in explicit coordinates? Well, if you introduce a Dirac spinor, then we have conditions like this one. Psi bar means proper automorphism to make everything work nicely. Well, first of all, they're null. Well, in this case, we have trialities, and the null is vectors after triality. Then we have, so this is psi Dirac. Then we have this condition. The condition means that two planes intersect by something that is bigger than linear space. This means they intersect by something bigger than a point. This means they intersect by something bigger than two-dimensional space. And finally, this will be non-zero. And this for you will be 3-form, coordinate components of 3-form, which correspond to G-orbit of this guy. So in physics, these things are known very well. This is called pure spinor conditions. So our spinors are pure spinors. And in fact, all vectors are what is called pure vectors, or tensors. By definition, pure tensor is a tensor who is on G-orbit of its highest weight. It's a definition, and it's equivalent of saying that it's a point on a parabolic flat manifold. That's what it is. Okay. Yes.
So this is exactly the number, right? In the beginning, you have simple reflection, linking diagram, and here, then you extend it to just the general picture of closures of supersymmetric.
Well, I'm not speaking. Yes, I mean we will need this.
The number of readers will be W.
Yes, this is correct. This is correct, but this is exactly warning. I need a different language. This language will mislead us. And this is important. You think it's equivalent, but there is something else happening.
I never saw anything like
Okay. Yeah. I mean, so, yes. So for the moment, you're right. Later, something else will happen. Yeah. So indeed. So this is this perpetrated by well group in reality, yes. Okay. So where we are now, right? So we know that we identify our parabolic subgroup. We found our quotient, and we need something which in physics called pure states in different sense. But in the sense, you know, I forgot, it's either Segre or Veronese embedding. I forgot who is who. Okay, so I just write it down. So let's consider two representations, L of omega A and L of omega B. And then we, of course, can do tensor product of them. And so what you need to do, what you can do, you can do projectivization in the beginning, or you can do projectivization after you take the tensor product. And so you can put here Cartesian product of two spaces, so you can do projectivization of tensor product. Yeah, and here we have coordinates. So let's say we have vector x with coordinate xi in the space L omega A, and vector y with coordinate yi in the space with coordinates omega b. So we have points here and points there. And so you can map them to points here by the following rule. Well, if you did tensor product in quantum mechanics, you know it really, really well. If you do it algebraic geometry, you also should know this, right? So what this point is a point which is pure state, which is one particle and other particles, they can be separated. But also we have mixed states which are not in the image of this product, right? And now, of course, here we have GPA, here we have GPB. So when A is only one index, it's called maximal parabolic subgroup because we have as many generators as possible without becoming the whole group. And this quotient is called Grassmannian. So when we have product of two Grassmannians, we want to ask how it's related to G quotient by PAB. And the question, can this be embedded here by this map? The answer is no. No. So if you have to implicit correlations, right? So arbitrary point here cannot arbitrary point in this product, which is subspace here, by this embedding map cannot be embedded here, right? Because here it can be one value of G acting on highest weight. Here can be another value of G, so they're not coherent. So in reality, embedding goes opposite way around. So here we consider this point as on G orbit of highest weight. It's easy to see that it belongs to the image of this embedding, and then we can pull it back, and then it will be this way. So correct way is to think in this way. Okay, and overall what we are going to need, we need maximal flag or just flag variety embedded into the product of all Grassmannians. This is the main object for us to consider today. So this is a big space, and inside the space there is a maximal flag G quotient B. And I'm going to parameterize points in the maximal flag as points in this space under this embedding. So explicitly, how it looks like. So if you speak about the case when G is a Salin, then we have flag point in the flag manifold can be considered as an ordered selection of R minus one vector of R vectors, and we parameterize it as a big vector here, V1 tensor V1 wedge V2 tensor and so on. Well, you got the point, right? This is how I parameterize it. So they satisfy all type of Kluge relations, and they have to satisfy a relation between themselves also to be in the image of this guy. So this is how I parameterize it. Now, exactly for Ivan's question, pay attention. For Salin, this is absolutely equivalent how you learn it using like Schubert calculus or whatever similar. Its coordinates here can be labeled by well group in reality. But when you do to other representations, we actually have points here which not on the Weil orbit of highest weight. So we have G orbit on the highest weight, but we also have Weil group orbit of highest weight. So you will find points that are not there. So for maximal flag, you do not need these points. You can solve them away. They contain no information. You can solve Kluge for them always. But if you want to consider Grassmannians, this point is actually important. And for the what I need to say this point should be there, otherwise it doesn't work. So this is a difference to what you might know from something else. Okay, very nice. So 25 minutes, or actually 35 minutes in my talk, I finished doing introduction. And now this is usual situation, right? And this is how science works these days. Now I'm capable to say something new. And this is what I'm going to do now. Okay. So we are going to consider. So finally, new stuff starts. We consider maps from our spectral space of where spectral parameter lives. Think about it as a strip. No need to do Riemann surfaces of genus G, just a strip. And we are going to map it to tensor product of all fundamental representations. So explicitly, this Q as a function of spectral parameter is just tensor product of a vector on the first representation, of a vector on the second representation, and so on. And now, first, let us do preliminary, let's say, kinematic constraint. Actually, I can completely skip it, but it's important to do it to understand what is going on. Q of u actually not arbitrary point here, but actually it should be inside this product. So this means that each vector is a generalized Plücke for corresponding Grassmannian. So all Q with small index vectors, they are pure vectors in the sense I explained. Yeah? So this is just to explain in which kinematic it works. And if you hear that the Baxter-P functions are Plücke coordinates and so on, this is the statement. And message, important message, if this was only the statement, we are far from done. Because it tells you not much yet. But now I'm writing a condition which tells you much more. Okay. So we have what is called fused flag condition. And let us formulate it. So let P1, PR be numbers such that the difference is plus or minus 1. If A is adjacent to B on the Dynkin diagram. So what we are doing with these numbers, we decide orientation of our Dynkin diagram, making two equivalent. So we can choose any quiver of shape of Dynkin diagram that we want. So like if we do this orientation, then number P here, if you choose it here, 0, then this node, because arrow goes this way, this node considered to be larger. So you have to put here P equal 1, then P equal 2, then P is equal to 3 here, and 1 again here. This is just example how you do it. It's just a way to decide orientation of Dynkin diagram. And so this is just a definition of orientation. And now, what is the condition that for any P, so you have to say for any orientation of Dynkin graph, Q shifted by this amount belongs to the maximal flag manifold. So this forms a maximal flag. So this is what is called fused flag condition. And if you guessed it, you guessed it right, because there is no other option. Big Q shifted by P means every single Q shifted by PA. That's what it means. Right? It's a little bit, so in the simple case, it's reduced to the y to the power omega in the character series. Yeah. So P somehow it's weight. Yeah. Okay, so this is a condition for any P. We have this property. And let me make two statements.
Interestingly, we consider orientations with one single additional condition. Any connected subset must contain unique minimum element. Then this immediately connected with sectors of KDB with many things.
So, yeah, so it's connected to, you don't imagine, let's discuss after the talk. It's amazingly connected to many things. I just, no, I wrote everything I need. There is no extra condition. Okay. Now first theorem conjecture. So theorem for AD and conjecture for E, that for any generic set of R functions, Q1 of U, QR of U. So notice these are not vectors, just functions. So there is no this brackets around. Exists unique up to symmetry fused flag Q such that Q first component of vector A is equal to A's function on the set. So what I'm saying that functional freedom of fused flag constraints is R functions. Using R functions corresponding to highest weight components, we can restore the whole stuff uniquely up to symmetries using fused flag constraints. So this theorem is main technical result. Actually, it is a hard theorem. You have to really go through all Dmytro diagram to prove it, or you have to do some other techniques. So this is hard technically hard part of the story. Technically not hard part of the story is that so theorem in generic position. This is quite straightforward actually. If U star is 0 of QA, so it means QA of U star is 0, and Q of U is regular at U star plus IZ over 2, then you can derive this following relation. So okay, let us discuss what I wrote now. So at least you have to understand the statement. Okay, no parameters, nothing is needed. So let us discuss. So at least you will get this message from this talk, and the rest we can discuss after the talk. So what I'm saying is the following. Let us pick our functions which exist in the strip, and some basically random functions. I mean, we can parameterize in a certain way, but I'm not going to discuss it. Then we can solve all the fused fast relations explicitly to get that this function is the first component on the fused flag. While solving these relations, we are going to have some Q functions which are singular outside of the strip. They always exist. In the strip, they will be analytic and nice. But outside this, they will be singular in principle. In principle, singular, right? So combinatorially, it's always possible, but to get singular functions. What I'm saying is that if actually zeros of original functions satisfy Bethe equations, then corresponding function should be regular corresponding point. So combinatorially, we can do always fused flag, but then if answer is regular enough, then it means actually Bethe equations were satisfied. This is the message. And now how we think about it from the point of analytic Bethe Ansatz plus plus. So the analytic Bethe Ansatz plus plus has two inputs. One, you say we have a fused flag. We have a fused flag, and the first term tells you that it's just saying that, well, it's always possible.
So these are parabolic Bethe Ansatz equations. You
Normal one, normal one. Yes. Now the physics comes to the following. We require that our maps from the spectral polarimeter plane to corresponding Grassmann manifolds, they have certain analytic properties. And depending, in particular, they should be regular maps. And condition of regularity is a very hard condition because this equation is self-consistently hard to satisfy. And then you actually have only finitely many such maps. And depending which analyticity properties you impose, you have different integrable models. And in some cases there are theorems, in some cases it's checked by insane amount of experiments. That number of solutions is exactly the spectrum of your model. There is no exception. So you can prove rigorous theorems, and for these guys you cannot prove rigorous theorems. And just one example of analytic ansatz is QA is equal to QA. This should be polynomial. So a vector whose components are polynomials. Then we have some function called dressing factor. And then we have some variables y to the power of Cartan acting on this vector to the power iu. And sigma a plus divided by sigma a minus product b adjacent to a. So these are Drinfeld polynomials that select for you representation of Yangian. So if you have Yangian and we have some its finite dimensional representation, in physics called spin chain. And this representation is labeled by Drinfeld polynomials. So if you Cook dressing factor satisfying this condition, this is just a bunch of gamma functions. And put ansatz on our functions Q in this way. So important part that then this is like defines your model, and this is what you want from analyticity. This guy should be polynomial maps. So sigma in reality CP1, and maps is regular polynomial. This is really what we want. Then requirement that the constructed fuse flux is actually have this structure give you precisely the spectrum of a rational spin chain, and in some case there is a theorem that it's exactly the spectrum, like it's like rigorous theorem. But in most cases it's just experimental fact. No, zeros of Drinfeld polynomials dictate your ansatz. And zeros of Q functions called beta zeros. Yeah? Okay, so this is how it works. And because I have to end up, let us come to the original problem. And let us say one simple statement. So let Q and P be fused flux. Then TAS convolution of QA shifted by S and PA shifted, PA star shifted by minus S is TAS. So what I written here is the following thing. So we have two fused flux of any type, any detail. We have a fundamental representation, vector in a fundamental representation, and vector in the contragradient of fundamental. These are dual representations, they can make convolutions. This is convolution. So the statement, if you do this convolution for any Q and P, this solves Hirota. So for those who knows, this can be interpreted as Q characters. So this is explicit expression infinite number of functions solving what very nice geometric properties of infinite system of equations on Q characters. So this is convolution. This is vector. This is dual vector. Yes, it's convolution between vector and dual vector. It's like scalar product if you wish. Yeah? This is just it. Yeah. So character is bilinear combination of Q functions. What you have to think about, Q is a wave function of solving Schrodinger equation, And scalar product between P is a Drinfeld polynomial which specifies representation of Yangian. Q should be thought as a wave function solving Schrödinger equation. And you know that scalar product of two wave functions give you observables in quantum mechanics. And this T is our observable, right? And we solve Hirota equation. And I will write one more formula and we'll stop. When I say Q characters, we have to slightly different formula. It's just one P special. We can choose special P. Namely, it will be Q shifted by Coxeter numbers. Okay. So experimental fact. If we have our analytic ansatz as written, then this stuff gives you eigenvalues of transfer matrices and rational spin chains. Like literally. Experimentally checked on computer. Well, in GLN, of course, many things are proven, but for us, for D series, we can do the game and it works. So there are much more interesting things that happen after, and you're welcome to discuss with me during lunch and after. So thank you.
Thank you very much. More questions?
So Hirota equation connected with integrable hierarchies like KP hierarchy. Do you know this? Of course.
Yes.
And except rational solution, we have also elliptic one. Have you any idea with which integrable spin chains it can be connected?
Okay. So first of all, about connection to KP hierarchy. So in reality, for this case, everything is simple because, well, for G series, this vectors Q are just exterior forms. And what's written here end up with being some big determinants. Well, and you know, then you can have all your stuff with fermions and whatever you want. I mean, it's just a bunch of Plucker relation between determinants. It's like encoded in this formula for GLN case. Now, for elliptic and whatever chains, I mean, so I'm trying to sell you some philosophy. What I'm saying, this is this term saying that actually to describe algebra of conserved charges, you have to do this nice geometric object, and it's universal. It doesn't depend on what you're doing. And then you have to guess correct analytic properties. So I'm a poor man. I know only two examples. One is the rational spin chain. I wrote it down here. And the other one is called the CFT integrable system. One is much, much more complicated, but I also know it. But then, because combinatorics is universal, well, you have to try guessing here, right? So this will be theta function like for elliptic case. And, well, you can start playing the game, which analytic properties you want. And I cannot answer the question which you will need for your complete system. So this I don't know. Yeah.
Thank you very much. So for the nice talk. So you mentioned spin change several times. So is this closed spin change you're talking about specifically?
Yes, closed periodic spin chains, and this is boundary condition for closed. It's twist.
Twist, I see.
Yeah.
And so do you see ways to extend this to descriptions of open spin chains? Like, do you have to maybe also some data related to a restricted root system or something like this?
Yeah, so you can do this by requiring special conditions with polynomials.
And would you get all possible?
I'm not sure that all, but some examples like exist. Yes.
Thank you.
Thank you very much. Other questions?
Sorry, maybe I am not ask your questions concerning of your work. Anyway, what you write, Q product of Q is product of 2Q is equal to product of many Qs. This is the famous Q systems, which was studied by many people, and it related with integrable system and so on. And some people maybe in particular case find solutions to this Q system. For example, Di Francesco, Kedem, and many other peoples, they find some special solutions to the Q systems. How it related with, is it some particular case of your considerations or not?
Yes, okay. So in literature there are, thank you for mentioning Di Francesco, that you know what Q system you refer to. So in community there are two Q systems. No, it's not Baxter, this is the point. One is called, what I'm doing is called QQ system in mathematics. And Q system is a character limit of Hirota when there is no plus and minus. So it's come from, I suppose, from Kuniba, who wrote, when plus and minus are absent, he replaced T with letter Q, and hence it's called Q system. So the answer is the following. What I'm doing is not Q system in the sense. What I'm doing is called QQ system in mathematics, although we called it for 10 years Q system with one Q. But we can still remove plus and minus. To remove plus and minus, what we have to, this formula will work if I just remove, if this guy is just an identity here for some Q functions, what we're going to have is character solution. So here you spit out characters of some representations which will solve your Q system. So you have to think about some special limit. I can say you one more thing. If you do Y system here and do Y system mutations, you can, for instance, see immediately the homology of periodicity from this formalism. So this will work. So we're not doing Q system in that sense, but we can generate some results there as a special case. Yeah.
Other questions?
So, of course, Y system is a generalization of ordinary Q systems. So you know how to construct Y systems for in your context. This is should correspond to thermodynamical methods.
Yes, okay. So that's what I said in words. Now we'll write formula. TAS is equal to TAS plus 1, TAS minus 1, divided by product of TBS. So Y functions defined in this way solve Y system equations which appear in terminal bit ansatz or in cluster mutation algebras. I mean, choose what your favorite. And if T solve Hirota, Y solve Y system. And hence this also solve Y system. And in particular, you see here a Coxeter. So in reality, if you impose conditions that Q of H plus 2 is equal to Q A star, up to some automorphism which you have to impose, of course, then your S direction will become periodic, and this is famous rank plus level periodicity, which you know for mutations on the corresponding cluster. So you can see it immediately there. Yeah. So yes, this is one historical fact. We want to solve TBA as well, and there are examples when we do it. Yeah. Yeah.
Sorry, do you mean periodicity is just generalization of a famous Zamolodchikov result?
Yes, it's not generalization. It is literally it. It is literally Zamolodchikov periodicity. Yes. Yeah.
Okay, let's thank the speaker. Thank you very much.